Good morning, students, and welcome again to the Physics of Music Part 4. As we mentioned earlier, our objective today is to explain the resonance that happens in a string. So, if we have a string on an instrument, in this case it will be fixed from both sides. So, I will have notes at both ends. So it's similar to an open pipe. Open pipe also have nodes at both ends. The length will be given as you see in the following equation. L, which is the length of the string, equals N represent the number of the multiples, half of the wavelength. Therefore, the wavelength is equal to, again, N, which is the multiple of what? 2L. And the frequency is going to be, as we knew before, F equal V over lambda. Now, N could be 1, 2, 3, 4, any number, because the harmonics are available at a whole number. For example, here, this is the fundamental frequency, or we call it the first harmonic. Lambda 1, which represents the first harmonic, equals 2L. Therefore, the frequency of the first harmonic, or the fundamental frequency, is going to be equal to V, and V is the speed of the sound divided by the first wavelength, or the wavelength at the fundamental frequency. Now, if I'm going to have the second harmonic, in this case, as you see, lambda 2, it means that it's the second harmonic, equals L, which makes the frequency of the second harmonic equal to V over L. Eventually, I will find out that the frequency of the second harmonic is twice the fundamental frequency. Now, if we go to the third harmonic, as we see here, the third harmonics will have 3 antinodes. So, the frequency on the third harmonic is 3 times the fundamental frequency. The speed of a wave on a string depends on the tension of the string. This makes it possible to tune the stringed instruments. You see here, we have the guitar, and these are the strings of the guitar. So if I wanted to increase the tension, I can just do it by adjusting these knobs. The tighter the string, the faster the wave moves along it, and therefore the higher frequency of its standing wave. Because strings are so small in cross-section area, so when they vibrate, they move very little air around them. This makes it necessary to attach them to a surrounding board, which makes or which transfers their vibration to the air and produce a stronger sound wave. So, for example, here do you see the wooden body of the instrument? The wooden body of the instrument is used as an amplifier. Let's learn more in this video.
electric guitar. An obvious application of physics to music, and it's an excellent tool for engaging your students in how physics applies to their everyday life. So let's study it. Now, the electrical guitar is still a guitar, and so before we study its electrical components, we need to first learn the general physics of guitars. Any plucked string on any guitar vibrates at several frequencies at once. Take a look. The note you're trying to play is called the first harmonic, or fundamental, and it looks like this. At twice the frequency is the second harmonic, and it looks like this. Again, at thrice the frequency is the third harmonic, which vibrates like this. You can prove that the higher harmonics are actually in the string by putting your finger where the note is supposed to be. Or you can start with your finger on the node and gently pluck. The wavelength of the second harmonic is the same as the length of the string, but the fundamental vibration doesn't even fit on the string. We have to imagine the rest of the wave, one up and one down. Therefore, the wavelength of the fundamental is twice the length of the string. The idea of tension of a wave on a string can easily be appreciated by taking a cardboard box and stretching a rubber band across it and plucking it. You can do this on a guitar too. Now you can understand how a whammy bar works. It reduces the frequency by lowering the tension.